In this video, we're going to be talking about sets, and more specifically, the Java collections version of sets. This can apply to C++'s standard library and Python as well. And this is just a overview of how sets work. Okay, so first, let's talk about what exactly a set is. Well, essentially, a set is a data structure or a container that's very similar to something like an array list. And array lists are basically just dynamic arrays. So in C++, this might be a vector, and in Python, it would just be a regular list. And it's different from array list because it uses something called hashing. And essentially, we're going to be talking about hashing in a little bit, but it begins empty, and elements can be inserted into the set or removed from the set. This is very similar to the array list or vectors or any list, but this is specifically different, and we'll look exactly why this is the case. So briefly, let's talk about hashing. Hashing is a type of encoding process that takes in an input and outputs a unique memory address. And essentially, the process of this encoding takes around O of 1 time. So I say approximately or around O of 1 time because it might have a few constants here and there that make it a little slower. But in general, we can say that it takes O of 1 time to process. Okay, so once again, back to sets. So the special property that makes it different from array lists is that repeated inserted elements do not appear more than once. They only appear once, right? So that means the set only contains unique elements. Now, one of the caveats or the little things that people might mess up is that the order in hash sets is not guaranteed. And this is not usually the case because the set that most other people think about is an implementation of a balanced binary search tree. But in this case, we're talking about hash sets. Okay. So we know that this property is useful for problems that deal with potential repeated information, or for problems that deal with the uniqueness of its elements. And we're also going to look at a few reasons we might use a set over an array list. Now, one example of this kind of problem might be, what is the number of distinct elements in a list? And this is a problem that we're going to go look over just in a little bit. Okay, now let's look at a few key operations that sets have, as well as their time complexities. So the first operation that we have is check if empty. So how do we check if a set is empty? Essentially what we can do is say st.isEmpty. And this is going to have a O of 1 runtime. Now the type can be any type, but the return type of isEmpty will be Boolean. Next, we're going to get getSize, and this is implemented using st.size. And this will run in O of 1 time. This essentially just returns the size of our current set, and this will be of type integer. The next operation is check if element exists, and this operation can be implemented using st.contains, and then the element that you want to see whether or not exists. Make sure that the element that you check whether or not exists is the same data type as the type you specified for the hash set. This will run in O of 1 time. Now, this is completely different from an array list in which the .contains method runs in O of n time because it needs to search through the entire list. But with sets, because it uses this kind of hashing, it's able to retrieve the memory address, right, of this element E in O of 1 time. And if it isn't able to retrieve it, then it'll return false, right? The next one is insert an element and it can be implemented using st.add e. It's approximately O of 1 time once again, and it might have a few constants here and there that make it a little slower. But in general, we call it O of 1 time. The last and final operation that we have is remove an element. So we have st.remove e, which takes around O of 1 time. Now it uses O of 1 time because it doesn't need to resize itself. It simply uses this idea of hashing, of storing the information in memory addresses, and it's able to do all of these operations in O of 1 time. Okay, so now let's look at an example where the power of sets can be fully captured. Okay, and the example I'm going to give you guys is not a too difficult one. And it states, given a list of n elements, where n is between 1 and 100,000, and we're given that these are positive integers, less than or equal to 10 to the 9, print out how many distinct numbers exist. So let's look at an example where n is equal to 2, so we have 2 elements, and let's say the elements were 1 and 2. Well, the number of distinct elements in this case would just be 2. Next, let's look at another example where n is equal to 4, and the elements that were given are 1, 2, 2, and 5. Well, the number of distinct elements in this case would just be 3, the 1, 2, and the 5. Okay, so first, let's come up with an idea or a solution to this problem using array lists or vectors or any type of array. So what's our initial solution? Well, number one, let's create an array list that stores numbers that we've already seen. So these numbers that we've already seen are going to be the elements so far, right? And it's not going to have repeated elements. It's just going to have numbers that we've seen so far. Next, for each element, we check whether or not we've seen it already. So for each element, as we're looping through that list of numbers, check whether or not it's in that array list. And if we haven't seen it already, well then let's add it to our list that stores the numbers we've already seen, and increase a counter by 1, which is going to be the total number of unique elements. And otherwise, if we have seen it, then we don't have to do anything. All right, so that's our initial solution. Let's code it up. So for our initial solution, we might have some sample input here as 2 and then 1, 2, which is we have 2 elements, and these are the elements. There's going to be 2 unique elements here. In this case, we have 4 elements, 1, 2, 2, and 5, and we have the answer of 3 unique elements. Okay, so let's try to implement this together. So first, we have an integer n, which is the number of elements. And then let's say we had an array nums. Let's take an input for that array nums. So nums_i is equal to sc.nextInt. And from there, what we're going to do is we're going to create that array list of numbers we've already seen. And it's going to be of type integer in this case, because we're storing integers. Let's call it seen, just so that we know exactly what we're trying to specify in this array list. So once again, this array list stores numbers we've already seen. We're going to store an answer as well. And this answer is just going to be the total number of unique elements in our list. So let's loop through it. All the elements stored in the nums array. And what we're going to do is we're going to create a Boolean, and let's call it already in seen. So we want to see whether or not that element I at an index I has already been seen. Let's assume that it's false at first, but as we search through the seen array, we're going to say if seen.getJ, right, the jth element in the seen array is equal to nums_i, Then already in scene is equal to true now, and we can break out of this J for loop here. Then if we haven't already seen it, so if it's not already in the scene array, then scene.add numzi, and we can increase our counter or our answer variable by 1. Finally, let's print that answer out, and let's test the code. So as you can see, we get all correct. All right, cool. Okay, so now what we should notice is that this, however, runs in O of n squared time, right? Which is too slow since n can go up to 100,000, right? And if we're given 1 second, well, O of n squared solutions for numbers up to 100,000 do not work. O of n squared might work between 1 and 1,000, but definitely not somewhere for, 100,000. Now, instead, let's make use of the unique ability of the set container to be able to only store unique elements with O of 1 inserts, right? So we're going to insert an element. It takes O of 1 time. But if we've already seen that element, it's not going to be added to the container. It's going to remain there, and no updates are going to change the set container. And so once we're done inserting all the elements, the set will only contain unique elements. All right, so let's code it up. Okay, so once again, we're given the same sample input and the same sample output. So what I'm going to do first is let's actually take in that integer n. This is the number of numbers that we have. Then what we're going to do is we're just going to create that hash set initially. The reason we really don't need to store the information anymore, the array itself, is simply because it's kind of useless. In the previous implementation, we also didn't really need to store the numbers as well. Instead, I want to show you guys how short the code could have been, right, if we didn't take in the input and stored it in an array. So let's take for each number, let's call that a substitute number, for example, m. And what we're going to do is we're just going to insert it into our set here. So we're just going to say st.addm. And now after we've inserted all the elements, it's only going to contain unique elements. And therefore, the size, right, the size of our set is simply going to be the number of unique elements in our list. And there you go. As you can see, it works. And that's pretty much it. So as you can see, this will run in approximately O of n time, because for each iteration from 0 to n minus 1, it'll take O of 1 time for all elements to be inserted. And since the hash set guarantees that the items will be unique, right, we know that the size of the set will be the number of unique elements in our list. And so in this video, you learned about hash sets, the time complexity of inserting, removing, getting the size, checking if it's empty, checking whether or not it contains a certain element, and that's pretty much it.